Welcome to this walkthrough of LeetCode problem number 1444, number of ways of cutting a pizza. In this problem, we'll explore how to divide a pizza grid into K pieces, ensuring each piece contains at least one apple. We'll discuss the problem requirements, break it down step by step, and analyze the solution. Let's dive in. In this problem, you are working with a rectangular pizza that is represented as a grid of characters. The grid contains cells marked with either a representing an apple or dot representing an empty space. Your goal is to cut the pizza into exactly K pieces, where each piece must have at least one apple. The possible cuts are either horizontal or vertical, and you can make multiple cuts to divide the pizza. The main objective is to determine the total number of valid ways to cut the pizza into K pieces, while ensuring each piece contains at least one apple. Since the number of ways can grow very large, the result must be returned modulo 10 to the power of 9 plus 7. The input includes the pizza grid as a list of strings, where each string represents a row, and an integer k indicating the number of pieces to divide the pizza into. The output is a single integer representing the count of valid cutting arrangements. Let's look at an example to understand this better. Suppose the pizza grid is given as A, AAA, and K is 3, meaning we need to divide the pizza into 3 pieces. The output for this example is 3, as there are exactly 3 ways to make the cuts. The first way is to make a horizontal cut after the first row and then a vertical cut after the first column. The second way is to start with a vertical cut after the first column and then make a horizontal cut after the first row. The third way is to make a vertical cut after the second column first, followed by a horizontal cut after the first row. In all these cases, each of the 3 resulting pieces contains at least one apple. Now, consider another example where the pizza grid is A, and K is 1. In this case, the output is simply 1. Since the number of pieces required is only 1, no cuts are needed at all. The entire pizza is considered as one piece, and it already contains apples, so the condition is satisfied. This is a straightforward scenario where no cutting decisions are necessary. On the other hand, if we take a more complex example like A, and set K to 5, the output becomes 8. This means there are 8 distinct ways to divide the pizza into 5 pieces, ensuring that each piece has at least one apple. The cutting configurations can vary significantly, but all of them must meet the required condition. To understand the constraints, let's consider the size of the pizza and the rules for cutting. The grid can be as small as 1 by 1 or as large as 50 by 50, and each cell in the grid is either an apple or empty. You can make up to 10 cuts, as specified by the maximum value of k. Importantly, every piece must contain at least one apple, so you cannot make invalid cuts that leave any piece completely empty. The result must be returned modulo 10 to the power of 9 plus 7 to handle large numbers. For edge cases, think about minimal inputs, like a single-cell pizza with one apple and k equal to 1. In this case, there's only one way, as no cuts are needed. Other scenarios to consider include pizzas where all apples are in a single row or column. For example, if the pizza is quad A and k is 3, you must make vertical cuts to ensure each piece has an apple. On the other hand, sparse distributions of apples, like A, with k equal to 2, require strategic cuts to ensure every piece has at least one apple. Finally, there are cases where no valid cuts are possible, such as a pizza with no apples at all. For example, with and k equal to 2, the result is 0 because it's impossible to divide the pizza and satisfy the condition. These edge cases demonstrate the importance of carefully analyzing the apple distribution and the cutting strategy. To solve problem number 1444, our goal is to divide a pizza grid into exactly K pieces, ensuring that each piece contains at least one apple. A natural starting point is the brute force approach. The intuition here is straightforward: generate all possible ways to cut the pizza into K pieces and verify that each resulting piece satisfies the condition of containing at least one apple. This can be implemented by recursively exploring all possible horizontal and vertical cuts, and after each cut, validating the resulting subgrids to ensure they meet the criteria. However, the major drawback is the sheer number of possibilities. For an MXN grid, the number of potential cuts grows exponentially, and validating each piece further adds to the computational cost. This results in a time complexity that can easily reach O(2) m plus n*k, making the brute force approach impractical for larger grids. While conceptually simple, it quickly becomes infeasible as the grid size or the value of k increases. To address the inefficiencies of brute force, we turn to an optimized dynamic programming approach, enhanced by pre-computing a prefix sum array. The intuition here is to break the problem into smaller subproblems and solve them recursively, leveraging memoization to avoid redundant calculations. A key observation is that the state of the problem is defined by the position of the current subgrid and the remaining number of cuts. By pre-computing the apple counts for all possible subgrids using a prefix sum array, we can validate whether a subgrid contains apples in constant time, significantly speeding up the process. The DP state can be defined as dp, I, j, k, representing the number of ways to divide the grid starting from the top left corner, I, j, with k cuts remaining. Transitions occur by making either horizontal or vertical cuts and recursively solving for the remaining pieces. The base case is simple. When k equals 1, we simply check if the current subgrid contains apples. This approach has a complexity of O, k times m squared times n plus k times m times n squared, which is feasible for moderate grid sizes, particularly when compared to the exponential complexity of brute force. After evaluating the options, we chose the optimized dynamic programming approach with pre-computation as our strategy due to its balance of efficiency and scalability. The prefix sum array was a critical component, allowing us to validate subgrids in constant time, which drastically reduced the overhead of repeatedly checking for apples. The recursive DP formulation ensured that we computed results only for unique states, avoiding redundant calculations and improving runtime efficiency. One key insight, or aha moment, was recognizing that pre-computing the prefix sum array not only simplified the problem but also made the solution scalable to larger grids and higher values of k. Of course, there were trade-offs. While brute force was simpler to conceptualize, its exponential growth rendered it impractical for anything but the smallest grids. On the other hand, the DP approach, while slightly more complex to implement, proved to be significantly faster and better suited for handling the constraints of the problem. By combining these elements, we arrived at a solution that is both correct and efficient, striking the right balance between implementation complexity and runtime performance. To solve the problem of cutting a pizza grid into exactly k pieces where each piece contains at least one apple, we need an efficient approach. The first step in our algorithm is to pre-compute the apple counts for all subregions of the grid. This is achieved using a 2D prefix sum array, which helps us quickly determine the number of apples in any given subgrid. We construct the prefix array by traversing the grid from the bottom right corner upwards and to the left. For each cell, I, j, we compute the sum of apples in the subgrid spanning from I, j, to the bottom right corner using the formula, the current cell value plus the sums from the row below, the column to the right, minus the overlap from the bottom right diagonal. This ensures that all subgrid apple counts can be queried in constant time during the dynamic programming process. Efficient subgrid calculations like this are vital for keeping the algorithm performant. Once the prefix sum array is ready, we define our dynamic programming state. The state dp, k, r, c represents the number of ways to cut the subgrid starting at cell r, c into k pieces, ensuring each piece has at least one apple. For the base case, if k equals 1, the answer is simple. Return 1 if the subgrid contains apples, otherwise return 0. For the recursive case, when k is greater than 1, we need to explore all valid ways to make a single cut. This involves two options, horizontal cuts and vertical cuts. For horizontal cuts, we try cutting below each row and check that both the top and bottom subgrids are valid. Similarly, for vertical cuts, we try cutting to the right of each column and ensure the left and right subgrids are valid. The total number of ways is the sum of all valid cuts, which is stored in dp, k, r, c. To avoid redundant calculations, we use memoization, caching results for each combination of k, r, and c. This ensures we don't recompute the same state multiple times, significantly improving efficiency. Several key insights drive the efficiency of this algorithm. First, the 2D prefix sum array allows us to check whether a subgrid contains apples in constant time, which is critical given the number of subgrid calculations we perform. Second, the recursive division of the grid into smaller subgrids with k1 pieces follows a divide-and-conquer approach, making the problem more manageable. Third, we can prune invalid states early on if a subgrid has no apples, we immediately return 0, skipping unnecessary computations. Finally, as the results of the calculations can grow quickly, we apply the modulo operation with 10⁻9 plus 7 at each step to keep the numbers within a manageable range. In terms of data structures, the algorithm relies on the prefix sum array for efficient apple counts and a 3D array or dictionary to cache the DP values for each state. Together, these structures enable a time complexity of O, k*m*n*, m plus n, which is feasible for the given constraints. Let's analyze the complexity of this algorithm. The time complexity starts with O, m*n, for constructing the prefix sum array. The dynamic programming computation involves exploring potential cuts for each state, k, r, c. For a given state, we may explore up to O, m plus n, cuts, and since there are O, k*m*n, total states, the overall complexity becomes O, k*m*n*, m plus n. For space complexity, the prefix sum array takes O, m*n, while the memoized DP table requires O, k*m*n, making the total space complexity O, k*m*n. Lastly, we handle several edge cases. If there are no apples in the grid, we return 0 immediately. If k equals 1, we ensure the entire grid contains at least one apple. Finally, if the number of pieces, k, exceeds the number of cells in the grid, it's impossible to make such cuts, so we return 0. These considerations help ensure the algorithm is robust and handles all scenarios effectively. Here, we begin by importing the ru_cache decorator from the functools module, which we'll use to optimize our recursive function. Inside the solution class, we define the ways method that takes the pizza grid and the number of cuts, k, as inputs. First, we determine the dimensions of the pizza grid, m4 rows and n4 columns, and define a constant mod to handle large numbers for our output. To efficiently check for apples in any subregion, we pre-compute a prefix sum array called apples. This 2D array stores the cumulative count of apples in every subregion of the pizza grid, starting from the bottom right corner. Using nested loops, we iterate over the grid in reverse order and update each cell based on whether it contains an apple and the sums of the regions to its right, below, and bottom right diagonal. This allows us to quickly calculate the number of apples in any rectangular region later. Next, we define the helper function has_apples, which checks if a given subregion contains any apples using the prefix sum array. This is a key utility for determining whether a piece of pizza is valid. Finally, we set up our memoized recursive function dp, which takes the current position, x, y, and the remaining number of cuts as arguments. If no cuts are left, we simply check whether the current region contains apples and return 1 if it does, or 0 otherwise. We also initialize total_ways to accumulate the number of valid ways to make the cuts. To calculate the number of ways to cut the pizza, we first consider horizontal cuts. Using a loop, we iterate over all possible rows below the current position, x, y, where a horizontal cut can be made. For each potential cut, we check if the upper region contains at least one apple using the has_apples function. If it does, we recursively call the dp function, passing the new starting row and reducing the number of remaining cuts by 1. The result is added to total_ways, and we ensure the value stays within the bounds of mod by taking the modulo after each addition. Similarly, we handle vertical cuts by iterating over all possible columns to the right of the current position. For each potential vertical cut, we check if the left region contains apples. If valid, we make another recursive call to dp with the updated column index and one fewer cut. Again, the result is added to total_ways, followed by the modulo operation. Finally, we return the total number of ways to cut the pizza, starting from the top left corner, 0, 0, with k1 cuts remaining. This approach ensures that we explore all valid combinations of horizontal and vertical cuts while leveraging memoization to avoid redundant calculations and improve efficiency. Here, we start with the Java implementation of the solution. First, we import necessary libraries and define a constant mod to handle large numbers during modular arithmetic. The main function, ways, accepts the pizza grid as a list of strings and the number of slices, k. We extract the dimensions of the pizza grid, m and n, and then pre-compute a 2D prefix sum array called apples. This array helps us quickly calculate the number of apples in any rectangular subregion of the pizza. To build this array, we iterate backward through the grid, summing the apples in the current cell and the already computed values from neighboring cells to the right and below, while subtracting the overlapping region. After constructing the prefix sum, we set up a 3D memoization table to store intermediate results for our dynamic programming approach. The function then calls the helper method dp, starting from the top left corner, with k1 cuts remaining. In the dp method, we first check if the state has already been computed in the memo table. If it has, we simply return the stored value. Next, if no cuts are left, we verify if the current piece of pizza contains any apples using the hasApples helper method. If it does, we return 1, indicating a valid way to slice the pizza, otherwise, we return 0. We then initialize a variable total ways to accumulate the number of valid ways to make the cuts. For horizontal cuts, we iterate through possible row indices below the current row. If the upper segment contains apples, we recursively call dp for the remaining cuts. Similarly, we handle vertical cuts by iterating through column indices to the right of the current column, ensuring the left segment has apples before making a recursive call. Finally, we store the result in the memo table and return total ways, ensuring the value remains within bounds using modular arithmetic. The helper method hasApples calculates whether a subregion contains apples by leveraging the prefix sum array, making these checks efficient. To solve this problem, we start with a simple example where the pizza is represented as a 3x3 grid and we need to make 3 cuts. The first step is to pre-compute the apples array using prefix sums. This array helps us determine the number of apples in any rectangular region of the pizza. The computation is done from bottom right to top left, ensuring that each cell in the apples array accounts for the current cell, the cells below, the cells to the right, and avoids double counting the overlap. For instance, apples 2, 2 gives the number of apples in the bottom right corner of the pizza. After processing the entire grid, the apples array for this example becomes 4, 3, 1, 0, 3, 3, 1, 0, 1, 1, 0, 0, 0, 0, 0, 0. Next, we define the recursive dp function dp, x, y, cuts, which calculates the number of ways to make the remaining cuts starting from the top left corner of the pizza. We initialize it with dp, 0, 0, 2, representing all 3 cuts minus 1. Horizontal cuts are considered first, such as cutting after row 0, checking if the top portion contains apples, and proceeding with the recursive call dp, 1, 0, 1 if it does. Horizontal cuts can also occur after row 1, where we verify if the top 2 rows contain apples and then call dp, 2, 0, 1 for the remaining cuts. Similarly, vertical cuts are evaluated, such as cutting after column 0 and checking if the left portion of the pizza has apples. If true, we proceed with dp, 0, 1, 1. Likewise, cutting after column 1 is considered, leading to the recursive call dp, 0, 2, 1. The base case in our function is when no cuts remain. If there are no apples in the current region, the function returns 0, otherwise, it returns 1, as no further division is needed. Intermediate results are calculated in cache to prevent redundant computations. For example, dp, 1, 0, 1 evaluates to 2 ways, while dp, 0, 1, 1 results in 1 way. Combining all these, the total number of ways for dp, 0, 0, 2 is 3, which corresponds to the output for this example. Now, let's look at an edge case where the pizza is entirely filled with apples and we need to make just 2 cuts. The pizza is represented as a 2x4 grid, and the pre-computed apples array shows the cumulative count of apples in each rectangular region. Here, the apples array is calculated as 8, 6, 4, 2, 0, 4, 4, 4, 2, 0, 0, 0, 0, 0, 0. With this setup, we begin with dp, 0, 0, 1 representing 1 remaining cut. A horizontal cut after row 0 is evaluated first, where the top row contains apples, leading to the recursive call dp, 1, 0, 0. Similarly, a vertical cut after column 0 is checked, and since the leftmost column has apples, we proceed with dp, 0, 1, 0. These calls allow us to evaluate the number of valid divisions for this configuration. In the base case of this example, dp, 1, 0, 0 returns 1 because there are apples in the bottom row, making it a valid division. Similarly, dp, 0, 1, 0 also returns 1, as the remaining region in the right columns contains apples. Adding these results gives a total of 2 ways to cut the pizza for dp 0, 0, 1. This is the output for this edge case. Now, consider another example where there are no apples on the pizza, represented as a 2 by 3 grid with k equals 1. Since no cuts are needed, we directly check whether the entire pizza contains apples. For this example with no apples, the apples array is pre-computed, but all its entries are 0 because there are no apples anywhere on the pizza. When evaluating dp 0, 0, 0, which checks if the entire region from the top left to the bottom right contains apples, the result is 0, as there are none. Therefore, no valid way to cut the pizza exists, and the output is 0. This demonstrates how the solution handles cases where the pizza lacks apples entirely. To analyze the time complexity of our solution, we start with the pre-computation of the prefix sum table, called apples. This table helps us determine the number of apples in any rectangular subregion of the pizza. Since we have a grid with m rows and n columns, we compute this table by iterating through each cell, and each computation runs in constant time. This gives us a time complexity of O, m*n for this step. Next, we have the recursive function dp, x, y, cuts, which calculates the number of ways to cut the pizza starting from a specific position, x, y, with a given number of remaining cuts. The total number of valid states for this function is bounded by O, m*n*k, where k is the maximum number of cuts. For each of these states, we evaluate potential cuts using 2 loops. One loop handles horizontal cuts, iterating through rows, which in the worst case takes O, m. Similarly, the other loop handles vertical cuts, iterating through columns, which takes O, n in the worst case. Combining these loops, each state requires O, m plus n, time. This sets the stage for our total time complexity analysis. Now, to compute the total time complexity, we multiply the number of states, O, m*n*k, by the time taken to compute each state, O, m plus n. This results in an overall time complexity of O, k*m*n*, m plus n. Moving to space complexity, the first major contributor is the apples prefix sum table, which requires O, m*n, space to store the apple counts for each cell. The second component is the memoization cache used by the dp function. This cache stores results for all possible states, x, y, cuts, and since there are O, m*n*k states, the cache consumes O, m*n*k space. Finally, we account for the recursion stack. The depth of the recursion depends on the number of cuts, which is at most k. Each recursive call takes constant space, so the recursion stack requires O, k, space. These components together contribute to the overall space complexity. Combining all these factors, the total space complexity becomes O, m*n plus m*n*k plus k. Simplifying this expression, the dominant term is O, m*n*k. Comparing this optimized approach to a brute force solution highlights the efficiency gains. A naive solution would involve generating all possible ways to make k1 cuts, then validating each partition to check for apples. The number of possible ways to cut the pizza grows exponentially with the rows and columns, resulting in an exorbitant time complexity of O, 2 m plus n, in the worst case. In contrast, our dynamic programming approach drastically reduces the number of computations. By leveraging memoization and prefix sums, the number of states is limited to O, m*n*k, and the presence of apples in a subregion is checked in constant time. This transition from exponential to polynomial complexity demonstrates the power of the optimized solution. The improvement can be further justified by the key optimizations. Using the prefix sum table allows us to retrieve the number of apples in any subregion in O1 time, as opposed to recalculating the sum directly, which would take O, m*n, time. Additionally, memoization ensures that overlapping subproblems are computed only once, eliminating redundant calculations. Together, these techniques reduce the exponential complexity of the naive approach to polynomial time. Looking at different scenarios, in the best case, where k equals 1, no cuts are needed, and the solution simply checks whether the entire pizza contains apples. Here, the time complexity is dominated by the prefix sum pre-computation, which is O, m*n. In the worst case, when k is large, close to the total number of cells, the solution requires the maximum number of recursive calls and evaluations of potential cuts, leading to the highest time complexity of O, K asterisk M asterisk N asterisk, M plus N. In an average case, the complexity remains asymptotically the same, but the actual number of states and cuts evaluated depends on the distribution of apples and the value of K. Finally, we can validate the derived complexity mathematically. The total number of states, X, Y, cuts, is O, M asterisk N asterisk K, as it spans all possible starting positions and cut counts. For each state, evaluating potential horizontal and vertical cuts takes O, M plus N, time. By combining these, we confirm that the total time complexity is O, K asterisk M asterisk N asterisk, M plus N, derived by multiplying the number of states by the computation cost per state. Similarly, the space complexity is dominated by the memoization cache, which stores the results for O, M asterisk N asterisk K, states. This aligns with the derived space complexity of O, M asterisk N asterisk K. These results demonstrate that the algorithm is efficient and well-suited for solving the problem within reasonable constraints. When solving this problem, there are some common mistakes you'll want to avoid. First, it's crucial to handle the base cases in your dynamic programming solution correctly. Specifically, when K equals 1, you need to check if the remaining grid has at least one apple. If it doesn't, the result should be 0, as no valid cut can be made. Skipping this check might cause your code to produce incorrect results or even enter infinite recursion. Another frequent issue involves the misuse of prefix sums. Prefix sums are essential for quickly calculating the number of apples in any subgrid, but errors in initializing or updating the prefix sum array can lead to wrong apple counts. To prevent this, always test your prefix sum logic with small, simple examples. Additionally, failing to use memoization in a recursive solution can lead to overlapping subproblems, where the same calculations are repeated multiple times. This not only increases runtime but can also cause time limit exceeded errors. On top of that, slicing the pizza grid improperly could result in out-of-bound errors, especially with edge cases like a 1x1 grid or when the pizza has empty rows or columns. Lastly, ignoring edge cases, such as when K is greater than the total number of apples or when the entire grid is empty, might cause crashes or incorrect results. These are all critical points to keep in mind as you implement your solution. Now, let's focus on insights that are especially useful for interviews. A key concept in this problem is divide and conquer, breaking the pizza into smaller subgrids while ensuring that each piece contains at least one apple. This is where prefix sums become invaluable, as they allow you to calculate the number of apples in a subgrid in constant time. Additionally, you should emphasize the role of dynamic programming. The problem can be framed as a 3D DP, where dp, I, j, k, represents the number of ways to cut the pizza starting at cell I, j, with k pieces remaining. Managing the state transitions efficiently is vital to optimizing your solution. It's also important to understand the trade-offs involved. A brute force method, which checks all possible cuts, would quickly become infeasible for larger grids due to its exponential complexity. However, by leveraging memoization and prefix sums, you can reduce the complexity significantly to O, K times N squared times M. Finally, during interviews, you should be prepared to explain the logic behind your DP state transitions and how you calculate subgrid apple counts using prefix sums. These are common follow-up questions that interviewers might ask to assess your understanding of the problem and your optimization techniques. To deepen your understanding, it's helpful to explore related problems. For example, LeetCode number 221, maximal square, is another grid-based DP problem that shares a focus on subgrid calculations and prefix sums. Similarly, LeetCode number 1277, count square submatrices with all ones, involves efficient subgrid counting. LeetCode number 85, maximal rectangle, also uses prefix sums in the context of grid problems, and LeetCode number 363, max sum of rectangle no larger than k, focuses on submatrix sums with prefix sums. These problems can provide additional practice with similar techniques. As for alternative approaches, you might start with a brute force solution that recursively tries all possible horizontal and vertical cuts. While this approach is straightforward, its exponential complexity makes it impractical for larger grids. A more efficient method is to use recursion with memoization, which stores the results of previously computed subproblems to avoid redundant calculations. This significantly reduces the time complexity, though you must carefully handle edge cases. Another option is to use bottom-up dynamic programming, which builds the solution iteratively from smaller subproblems. This avoids issues with the recursion stack, but it can be more challenging to intuitively implement during an interview. Each of these approaches has its strengths and trade-offs, so understanding them will help you adapt your solution to different scenarios effectively. Great job! In this session, we tackled the number of ways of cutting a pizza problem using dynamic programming. We highlighted the importance of breaking down problems into smaller states and considering edge cases. Thanks for watching, and don't forget to like and subscribe for more content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!